All right. Hello, everyone, and welcome to CSE365. We are making our way through this course. We are starting now the fourth module. Who liked the third module? Did anyone like the third module? Oh, we got some hands. Who hated the third module? Too much assembly, or didn't like web servers? What's the issue?
Honestly, at the time I was wondering if it was the server
Uh-huh.
or
Some more feedback. Some more feedback coming from the challenge, you think, would be helpful?
Yeah.
Yeah, I think it's fair. Yeah. No, it's fair criticisms. Uh, all right. Well, fortunately, the third module is now in the past. We are entering the fourth module, and the fourth module is reverse. Oh, there's a question. We already got a question. Yes.
I have a question about the last
Yes. On building a web server? Yeah.
So I kept getting I forget exactly what the error was, but I asked Sensei what it was, and he was saying that I had to be handling a child because I kept getting like the error for like the socket's busy or something like that.
Like you were getting like busy or something?
Something like that. And it was telling me that I had to handle like the child, like the sick child.
So the very last level, I'm trying to remember the last level. Does it show you an strace output?
It does, but it doesn't show you what's expected. It just shows you.
It just shows you what happened.
One that like spams a bunch of requests, like post.
Right. So you were probably getting a signal that was like sig child, sig CHLD, right? So what's happening there is while it's tracing the process, every time one of the processes dies, so one of the child processes dies, the kernel automatically sends a signal to the parent saying sig child. And that's like one mechanism that you can detect that one of your children processes died is through signals. Alternatively, you can use that wait system call we talked about last week. I'm guessing that Sensei was confused, possibly, very possible. So I would need more specifics. If you want a message after class, like what exactly the error message was, I'd be happy to take a look at it and like finally figure out what the heck was happening. But I guess for the last level, prior to that, it was only ever one request, right? Was the last level specifically that was multiple requests?
Yeah. Last level was multiple. It's the last one was either.
Oh, it was get or right. So yeah, I'm wondering. So I know for sure a lot of people have troubles with that last challenge because it's the final one. In theory, that challenge, your solution for the last level should work on the previous level, and I think also the previous level, because I think previous is a bunch of gets, and then previous is a bunch of posts, and then last is get or post. So really, I think your solution between that's the last is 11. So between 9 and 10, it should be like 3 lines of assembly. So literally just, if you take your solution for 9 and you take your solution for 10, and at the very beginning, after you read in a request, you just check if that first character is a G or not a G. And then you just branch into your 9 solution or branch into your 10 solution. There's room for error in that process, but that's roughly speaking what it should look like. And then you should be able to take that solution and run it on 9 and it should work, and it should also work on 10. But yeah, feel free to message after the. Oh, you still got it.
I found what the error was, but it's fine.
Okay. Yeah, for sure. All right. So if one of the reasons you did not like building a web server was because assembly. Actually, quick show of hands. Who here would rather read C code versus assembly code? Let's start with C code.
You said rather what?
To understand what's happening. You'd rather look at assembly?
Yes.
Who would rather look at C? Who would rather look at assembly? All right. We got a couple hands for assembly, a lot more hands for C. Unfortunately for you, we will be reading assembly. And the reason we're going to be reading assembly is because, on average, It's easier to see like at a high level what the heck a program is doing with C. Now, if you want to get into the real nitty gritty of what it's doing, that's where assembly comes in. Assembly is like the truth. Technically, it's all just a tower of abstraction. Even assembly is a lie. Below assembly, there's this thing called microcode that's actually what's running. Technically, x86 is, I don't know, maybe you say x86 is running, maybe you don't say it's running. Below that on the abstraction tree, there's microcode that's running. Every x86 instruction gets converted into potentially multiple microcodes, but we're not going that deep down the ladder. So this module is going to be different though, fortunately. Instead of writing assembly, you're going to be reading assembly. Now, I don't know whether your instinct is to say that writing something is easier or reading something is easier. Unfortunately, probably reading it is more difficult. But you're going to learn a lot about what the heck's going on. And the idea of this is instead of building a web server, you're going to be analyzing a bunch of programs. So this module, actually one thing I'll point out is like a meta level. This module is kind of split into two submodules. You'll see the first opening levels are called debugging refresher. These levels are going to walk you through using GDB. And I believe, right up here, we talk about, debugging refresher versus the second half, which is reverse engineering. So we threw debugging refresher in there to make sure everyone's familiar with GDB going into this. And so, there's two little submodules. The first one, more GDB-esque. The second one, more like, give me a program and let's understand what this program does-esque. So that's the whole idea of reverse engineering. And specifically, there's a whole bunch of different tasks within reverse engineering. I would say, and I think a lot of people would say, even reading C source code is reverse engineering, right? If you have to understand what the heck a system does, it doesn't matter how it's expressed. Like at a high level, the purpose of reverse engineering is looking at some program, or really just some idea, and trying to understand how the heck does it work, and really understanding the design of it. And from a security mindset, understanding the flaws of it. So let's jump into it. So in fact, this test.c does not exist. This is fake. Okay, so all we have here is this test program. So the question is, this is some binary, some program. Our goal in reverse engineering, specifically in this case, we're focusing on binary reverse engineering. You don't have the source code, but you do have some artifact that is the thing that will run. You have a running copy of the system you're trying to analyze here. And in this case, if we use the file command, we know that what this thing is an elf. So we've previously talked a little bit about elves. They're the executable format on Linux. And when you run something like GCC on Linux, you're producing an elf. When you run AS and LD on Linux, as you did in the last module, you produce an elf. So right off the bat, we ran file on test, and it says, hey, this is an elf. If I instead look at, let's see here, etc password. So this is where a bunch of user information is stored. The file command says, hey, this is ASCII text. And if we cat etc password, this is what it looks like. So this is basically, if you're not familiar with etc password, this is listing a bunch of users on the system. So for example, root is a user. It has user ID 0. If you want to start up its default shell, that default shell is bin bash. Whole bunch of random users that don't really matter. There's this fun user called the nobody user. It's kind of fun. And more importantly, I guess to us, we have the hacker user. So that's user ID 1000. That's who we're running as. We can see here our home directory is home hacker. Our default shell has been bash. You could change your default shell. You could, I guess, change your home directory if you wanted to. And this file just lists out a whole bunch of stuff. This is not an ELF. This is very readable file. It's not necessarily intended for human consumption, but it is human readable. On the other hand, if I cat test, this is not a human readable file. I mean, maybe you're going to argue, what the heck is human readable? Probably you don't want to look at this. This isn't like how you would read and understand this file, right? We could cat it and we could see stuff, right? We can see a whole bunch of human readable stuff in here. So for example, underscore data underscore start is like something in here. But we got like a whole bunch of like non-ASCII bytes in here. And crucially, this is this machine compacted file. It's meant for machine use is really what this is meant for. Now, one program that can interact with this is cat. So cat obviously interacts with this file format, not very nicely, but it can ingest it and print something out. File interacts with this program. This is the file program kind of gives you, it has like kind of some signature matching on files and is able to detect information. So for example, the reason it knows it's an ELF is if we look at XXD, this is another program that could interact with this file. This is a hex dump. And we look at just the beginning of this file represented as bytes here and, ASCII, where ASCII appropriate here. You'll see this file just starts with 7F and then ELF in all capital letters. The way the file program works, at least as far as we're concerned, in its ability to detect that this is an ELF, is it just opens up this file, reads it, and one of its signature matches is, okay, this thing starts with 7F ELF, like this is an ELF file. And then it gets all this other information by parsing it further. So it turns out that within the structure of this file, there's something that effectively says, this is a dynamically linked program. It has this interpreter thing. It has a build ID built in here. It's not a stripped binary. So stripped binary is something where all the symbols are removed from it. So for example, underscore start is a symbol. If you used other labels in your program in the last module while you were assembling, all those labels were symbols. And when you write a C program and you have a bunch of functions, all those function names are symbols. You can remove all of those because it turns out those things don't matter for running it. It's just a bunch of addresses. No one cares about it. But by default, for example, something like GCC produces a not stripped binary. You can remove all those symbols, though, if you want to make the file a little bit smaller and less debuggable. So one of the other tools, right, that interacts with this file format, we've shown this in the past, was objdump. So specifically with this -D, this means disassemble. -M intel means show it to me as Intel style syntax. And if I put test here, I'm going to pipe this to less. This is probably, of what we've shown so far, one of the better ways of reading this file. So this is a much better method than cat for understanding. Remember, our goal right now is what the heck does this test program do? This is a great way to figure out what it does because guess what? We jump to main. Main is going to start giving us a bunch of x86 instructions. And these x86 instructions are telling us what this program is quite literally doing. The CPU is going to execute these instructions step by step. So this, maybe it's, as most people raise their hands, in preference to C, isn't your preferred way of understanding what the heck's happening. But this right here tells you exactly what this program does. Does anyone know what this program does just looking at it? Can someone say one fact just looking at this output, some statement of truth about what this program does? A quick thing you might hone in. Yeah, go for it. It's using the stack. That's true. Yep. The very first thing. Well, we've got this NBR64 instruction. You can think of this as a no-op. It doesn't really do anything. The very next instruction is push. Yeah, so we're definitely using the stack. So something that I hone in, and as you kind of go through this module, you realize a good thing to hone in on is the call instruction. The call instruction gives you a lot of information. As soon as you're calling something, like you've got some subtask you want to complete, well, now we know that main is doing some sort of subtask. And my mind immediately jumps to this call instruction right here. So we call printf. So if you've written C before, you know that printf is a way of outputting something to the screen. Crucially, before this printf instruction, another great thing to look for is jump if equal, jump not equal, compares control flow constructs. And if you look through all these instructions right here, Nothing before this call is a control flow instruction. There's no compare. There's no jump if not equal. There's no jump if equal. There's no jump if greater than. We've just got some stack manipulations. We got an XOR in here. We haven't talked a whole lot about a load effective address. It's similar-ish to a move. It's just instead we're grabbing this address rather than actually pulling out of memory. Can you guys be a little bit quiet, please? Thank you. And then we've got this call instruction. So this call is definitely going to happen. Looking at this objdump output, we don't know what the heck is being printed to the screen, except, we can work backwards from this call. What is the first argument to printf? Does anyone know the first argument to printf? Have you used printf in C before? It's like the thing you're going to print, right? Technically it's the format specifier, but it's the thing you're going to print. And the very first argument to printf, that goes in RDI. First argument goes in RDI. So if we work our way backwards from this call and look for something that manipulates RDI or EDI or some subset of the RDI register, and in this case we have this instruction right here, it's taking something to do with RIP, so the instruction pointer, plus this offset from the instruction pointer. So this is called RIP relative addressing. So it's very common to address things relative to the instruction pointer. It makes it kind of position independent in that if the data is always following your instructions, right, like they're sequentially in memory, if you know where your instruction pointer currently is and you know your data is at like plus 0x E1D away from it, you can reference data very nicely by going relative to the instruction pointer. And if you were writing this assembly yourself, you'd probably say, why would I want to do that? But think about it, right? It's GCC that's writing this assembly, not us. So GCC can go and do that math for us and figure out where the heck this thing is and do this RIP relative addressing. So whatever this is right here, this is what it's going to print to the screen. And then if we just look for more calls, right, then we call gets. Gets is going to get us some input. Then we can see a string compare, str compare in here. And I'm kind of like briefly looking, I guess right here we can see test and jump not equal. There's some sort of control flow in here. We got more calls. We got what more? We're just scrolling through this. We're kind of hoping in our head maybe this isn't thousands of instructions, right? And we're scrolling, we're looking at some compares, we're looking at some calls. We're not even like figuring out the flow of this yet. We're just like, really, I'm just looking for the calls. Like what the heck do we call in this thing? We got string compare, again, we got puts here, and then eventually we get read. So we're kind of like sigh of relief a little bit here that this main function isn't like thousands of instructions long. It's definitely some instructions, but it's not so bad, right? Like you probably wouldn't want to do this, but you could go through and think through the meaning of all of these instructions right here, right? This is like less than 100 instructions. You could work this out. Maybe it takes you a couple hours. Maybe it takes you 30 minutes, depending on how experienced you are. You could figure out what's going on here. Now, unfortunately, if you wanted to further understand what's going on, right, you have to follow through these calls. And if you really wanted to figure out what puts does, you can start reading the x86 instructions for the puts. And eventually you're going to start reaching syscalls and stuff. And then, if you want to keep digging in deeper, you could go and pull up the Linux source code for a syscall and start reading that. But at some point you can cut a boundary, right? We can say puts is a well-defined function. In fact, there's a man page for it, right? If I just do man puts, I don't need to go and reverse engineer by looking at x86 instructions, the puts function. This thing right here tells me what puts does. I don't need to do that by hand. I can read the nice documentation on it. Now, this is what would be referred to as static analysis. So what we just did is we started statically looking at this program. We took all the instructions and we didn't spend a whole lot of time, but we started just kind of reading some of them. At this point, just getting a high level overview of it, but you could dig in way deeper, follow the control flow, figure out what's really going on. The alternative to static analysis is dynamic analysis. So that's where you actually run the program. And one very simple version of dynamic analysis is literally just running the program. Maybe one step up from that is running the program under some sort of tool like GDB, or running it under some sort of tool like strace, where it's printing more information. So I don't know about you, but if I want to figure out what this program does, I probably don't actually want to start by reading the assembly. I would probably rather just like run the thing. I mean, assuming that we're not worried about it being like malicious or something and attacking my system and being a virus, because as soon as you run it, it could do whatever the heck it wants to do. But you're on the dojo, so worst case scenario, you affect the dojo with malware. Who cares? So we run this program, and okay, immediately like way more stuff about this program makes sense. Way better than reading x86. It says, let's play a guessing game, make a guess. So now I can just use like human intuition of like, what is this program? Well, this program seems to be a guessing game program. It's asking me to make a guess. And probably in my head right now, I'm thinking, especially, with the context of those string compares, but you don't even need to have statically analyzed this thing. You're probably guessing like, I'm going to make a guess and it's going to tell me if I'm right or wrong or something like that. So like human intuition on reverse engineering is very useful, right? Normally programs are designed for humans, or if they're not designed for humans and they're designed for computers, that somewhere along the chain, there's humans connecting into this computer system. And you should always keep that in mind. So if we just interact with this thing, let's say it says make a guess, let's just say test as our guess. Let's see what happens. It says you lose. So our first instinct, obviously, I wrote this thing. This is one of the difficult things about teaching reverse engineering, is that when you write the program, you're not really doing reverse engineering, right? I already know what this program does. But, maybe your intuition was correct, that it is going to say you lose, you win, whatever. So my goal might be to explore all of the paths that this program can take. In the case of this module, your goal in these reverse engineering things, we're going to have a whole bunch of key checkers. So basically, it is similar to this guessing game with some adjustments made, getting more and more difficult. Your goal is to guess the right thing, or not really to guess, to figure out the right thing. And when you win, it's going to print out the flag to you. So this is going to be the basic premise of this module once you get through these first 8 levels. All of these levels right here are going to be asking you to make a guess, to input the key. And when you input the key correctly, it will spit out the flag. So I could sit here for a while. I could think about a whole bunch of ways to approach this problem, right? There's a whole, I could just start guessing more things, secrets, the password, right? I could just maybe it needs a number. If I put a number to something different happen, I could start just interacting with this thing and see what happens. And that's, of course, an option. But as reverse engineers with access, this isn't a black box. So a very common term within reverse engineering, one kind of subset of reverse engineering is called black box reverse engineering. This is not a black box. We have the ability to introspect and see what the heck this thing is doing. Now, there's scenarios where you might be reverse engineering and you don't have access to the binary. Maybe you're connecting to something over the network. So, for example, you're connecting to some web server. Now, if you're connecting to a web server, you might not have access to the x86 of that web server or source code of it or whatever artifacts that kind of say what this thing is doing. But in our case, we have the thing. This thing right here, this file, which is only 17 kilobytes of data. This thing says everything that this program can do. Technically that's not true, right? You could imagine this thing loading in other files and doing all sorts of crazy stuff. But I'm going to tell you, it doesn't do that. So we're fortunate there. These 17 kilobytes of data say everything that this program does. And now it's up to us to figure out, how do we make the right guess? So one option is kind of think back to the web server. What system calls are being made? System calls provide a lot of information. So before we, go all in on reading a bunch of x86 instructions, we might as well at least like see what system calls this thing is making. So we'll run that, strace./test, and it turns out a whole bunch of system calls are being made. As you get more and more familiar with strace and stracing kind of real programs, or I guess where real means compiled by C programs, almost all of these at the beginning is the C runtime. So the C runtime is like loading in libc and stuff. And I'm going to tell you the secret. The secret to reading strace logs for something that was compiled from C is like just hone in on this brk system call. This brk system call is setting up the heap, and setting up the heap is one of the last things it does. So just skip past this. I'm not actually sure what the heck this fstat thing is doing. Probably that's some output mechanisms. I'm guessing that printf ultimately calls fstat for some reason. But basically just jump to brk and look past that. All this stuff before, this is just libc and the C runtime getting initialized. We don't care about that. In this case, if you were concerned, maybe you look into fstat. As you get experience, right, fstat is, we could look at it, man to fstat. This thing is like getting a file status. So maybe it's important that whatever file status it's getting, maybe that is relevant. While reverse engineering, though, I would say one of the crucial skills, and the only way you really learn this is by doing it, right? It's getting experience. But one of the crucial skills is figuring out what the best way is to manage your time. So as I said before, we could have just started by reading every single x86 instruction. But our goal is just like, right, to finish this module as fast as possible and be done with this assignment, right? That's our goal. We want to be efficient with our time. We don't want to just do this the slow and meticulous way. We want to be efficient. And so we need to figure out what we're just going to temporarily ignore. We'll like maybe make a mental note that like this fstat thing, maybe I need to investigate that once I've explored a bunch of paths and like nothing's making sense. Now I need to start digging into more details and figure out what the heck fstat does. But in my head, get file status, this is like, who cares, right? This probably isn't relevant. Really what I'm looking for here in this case, right, it says the write system call. So we're not maybe surprised by that, right? We're writing to file descriptor 1. Let's play a guessing game. How else did it appear on the screen? It made the write system call. And then it's reading something. So actually, if I run it again, I say test, then we can see what else happens. So it read in test, and then it writes you lose. So we write, we read, we write. So these are the system calls being made. Technically that fstat or whatever. These are the system calls being made. Turns out right now, the system calls aren't that interesting, right? This is probably, if you were going to write this program in x86 yourself and make some syscalls like you did in the last module, you would have done a write system call, you would have done a read system call, you would have done a write system call. For example, something maybe we were like thinking about is there some like password file somewhere? Did it open /temp/password and like read in a secret from that and then compare our guess with that? Well, it didn't. It didn't make an open system call and it didn't read from some open file system call. So we can be confident here that it is not reliant on some external file right now. It's not doing that. That's a very valid path. We don't know how this thing was constructed, and we wouldn't have known that just interacting with it. But looking at it from an strace perspective, we can say with 100% confidence that this thing is not opening some password file. So that is not something we need to figure out how to handle. At this point, we want to figure out why does it say you lose? And this is, if we think about it, and maybe, okay, so to be clear, there's one sad option that's possible. The sad option that's possible is similar to like what, level 6 or something of the web server where you just always say HTTP 1.1 200 OK or whatever, you just always 200 OK. There's a chance that whatever this program is, there's no control flow here. It just always prints out you lose. So this is an option, technically. There might be no answer that makes it say something other than you lose. But if we're optimistic and hoping maybe there's something we can do to make it say something other than you lose, that is there a different option is control flow. Control flow in a program determines, is there another option? And so what we're thinking in our head here is at some point we make a read system call. Now, technically, and as we saw before, and a write system call, as we saw before, it's not making read and write system calls. It's doing printf and scanf. Well, I guess we didn't see the scanf yet. Actually, there's no scanf. It uses gets, as it turns out. There's all these utility functions that will ultimately make the system call. So you got to start getting a little bit familiar with what are the C functions, for example, that are going to produce output? What are the C functions that are going to produce input if we're analyzing some C program? And we are in this case, it turns out. So we probably, and if we go back to objdump here for a moment, we want to see where the heck is it reading our input. So this call to printf here, this is probably, and we would have to figure out what RDI is at the moment it's doing printf to figure out for sure that this is the printf responsible for prompting us to make a guess. But we're just going to assume it is for a moment. The next thing it does, without control flow deviation, again, just LEA move between this call, and LEA is not a control flow instruction, is it calls gets. So gets, if you're not familiar, gets is a C function that can get input. So this is probably the guy that's doing give us input. Well, what happens after that? Well, again, only a few handful of instructions. In LEA, again, not a control flow instruction, LEA move. And then, okay, well, this is not a control flow instruction, but this is like a C function that's like ultimately doing control flow stuff. But we see the test and the jump not equal after the fact. It's stir compare. So in your head right now, stir compare is like, okay, we're on to something. We're trying to figure out what is the correct password. And simultaneously, the entire time you're like reverse engineering something, you're using human intuition, like this thing was built for a human. What the heck? What is the functionality here? And you should also be using kind of like a developer mindset. Like knowing what I already know about this program, how would I write this program? Well, if this is a password guessing game written in C and you're doing like printf and then you're doing gets, and then you're like, is the password correct? Well, in the land of C, probably what you're calling is stir compare. And we kind of hit the jackpot here. We're calling stir compare. Now, we don't know what we're comparing what with, but probably it's comparing whatever we input. Again, this is just a guess. We're like pruning the search space of what the heck this thing does and like honing in directions. Probably this is comparing our input with whatever the correct guess might be. Could be a lie. The stir compare could be comparing A with B and it's always false. We don't know until we want to really dive in, but probably at a high level, we're assuming that's the case. And we can see there's this branching behavior. So we test to see, test EAX. Basically, this right here is saying, okay, is the return value 0? So let me open another terminal. PS1 equals that. Man, what's it called? Stir compare. So if you're not familiar with stir compare, this is where you would do man stir compare and read the manual for stir compare. As the name implies, it compares two strings. And specifically, it compares two strings, S1 and S2. The locale is not taken into account. We don't really care about that. It returns an integer less than, equal to, or greater than 0 if S1 is found, respectively, to be less than, to match, or greater than S2. So we probably don't care about like what the heck is less than or what the heck is greater than. Turns out that's used for like if you want to sort a bunch of strings. Really, we're just asking, does it match or not? And the answer to that question is it 0 or not? If it's 0, if this documentation here says, if it's 0, these things match. And it also kind of inductively says, if it's not 0, they don't match. So when we look at this, this test EAX is basically saying, are these things equal to each other? Or really specifically, it's saying, is EAX 0? Test EAX is like, is this thing equal to 0? And then, I mean, maybe this jump instruction is more instructive of what's going on. It says jump not equal. So if these things are not equal, so in the fact that it turns out that this correlates exactly correctly with what we mean by match. If they're not equal, if the strings are not equal to each other, we're lucky that that kind of lines up nicely. If they're not equal to each other, then we're going off to main plus 0x62, so 122b. So 122b. So we would jump over to here. Otherwise, we're going to fall through. And fall through means do a load effective address, call puts. So here is an option, is that we can put something, and then this jumps off somewhere else, but we can definitely put something. So the control flow, right, starts to get a little complicated, but we're not going to focus too much on it, right? We're just honing in closer and closer to what's going on. And then otherwise we came over to this 122b option if they were not equal to each other. And we 122b, we take this thing, and then we immediately jump over here, I guess. So the control flow, it's kind of unfortunate, right, that like, you know, it would be really nice, like a graph. If a graph like showed the control flow. If you're thinking that right now, you're right, this would be very nice, and we're getting there. We're gonna have a tool that will build us a graph of the control flow, because following control flow linearly when it's like branching all over the place, that's a nightmare. But we're doing it momentarily. And then blah, 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 blah. We can see that there's another compare. We can see more stir compares. So at this point, right, I want to see what's going into this stir compare, right? That's the very first control flow thing. That's immediately, I don't know about you, I don't know, like that's what's on the top of my mind, is what's going into that first stir compare. We got RDI, we got RSI. At the point that we call stir compare, what's RDI, what's RSI? Like this is like top of the figure out what's going on in this program thing. So the simple answer to how do we answer what's going into stir compare at this time is to use GDB. We can run this program under GDB and inspect registers at any point in the program's flow. Let's go ahead and do that. So if we run gdb./test, and if you're not super familiar with GDB, don't worry, the first 8 levels are going to be giving you a nice primer on GDB, because GDB is a very useful tool for reverse engineering. So I start up this program, and if I print like 8 instructions, this is normally how I start. After I start something, I hit start I. I guess we didn't need to start I. We just did start. Start versus start I. In the assembly world, we were doing start I. Start is like a nicer start I. I know they're very close words, start and start I. Start just goes to main. Start I goes to _start. So that's the difference. In the assembly world, we couldn't do start because there is no main. So we had to do start I and go to the actual entry point. When we do start, it just breaks at main, and we're paused at main. It's very nice because, you know, in a C world, we just want to go to main. We don't need to watch _start, like initialize the C runtime and do all that stuff. Now, I also see this assembly syntax is terrible. So we're going to do set disassembly flavor Intel. Actually, as a quick aside, because we're going to do this a lot, this disassembly flavor Intel. If you always want it to be Intel flavor, which you probably do because that's all I use, so that's probably what you're used to seeing, and probably in the last few modules, all you've done is Intel syntax. If we want this to be permanent, what we can do is we can edit home hacker gdb init dot gdb init, and this file, what the code server is how we can like open up another editor. And if I just paste this in here, this .gdb_init file, and I just save it, every time GDB starts, it's going to run this command at the very beginning. So .gdb_init, if you've never heard of it, probably haven't, that's fine. Very useful for if you're running a command, literally every time you start GDB, put it in .gdb_init. Okay, now we can go ahead and gdb./test, we can start, we can xi RIP, and now we've got it in our Intel syntax. We didn't even have to tell it again to do that. So I want to break, if I hit enter, so I did x/8i, that means print 8 instructions at RIP, so where we're currently executing. And every time I hit enter, it's just going to show the next 8, and then the next 8, and then the next 8. We can do that, right? We can see a whole bunch of symbols are coming through, which is Interesting. That we didn't see before in objdump. We said we wanted to break at this first stir compare. Let's do that. We can just break. So what we can do if we want to break at this first stir compare, this is at main plus 75. We can break at main plus 75. So I think this is the right syntax. Break space star parentheses main plus 75. And we've set a breakpoint there. We could confirm that this 214 thing lines up, right? I think that should line up, but we'll show you, yeah, 214 lines up. You could have put the address itself also, star address, that would work. You could also break stir compare, like B space stir compare. The difference is that you would already be inside of stir compare. And it would break every time you ever hit a stir compare, which would totally be fine. That would work for us. And that would actually technically have been slightly simpler. In this case, though, we're breaking at this particular call to stir compare before the call happens. So there's like a subtle difference there. Both would work in this case, but we're specifically wanting to break at main plus 75 versus stir compare because that's what I decided in my head that I wanted to break at. So if we continue now, we don't have to step through these instructions one at a time. We don't care. We just want to answer the question. What the heck is an RDI? What the heck is an RSI? Continue. Okay, so we're in GDB. GDB is also printing the program standard out and taking in standard in simultaneously when you're not in this interactive part. And as soon as I continue means go until I hit a breakpoint. So it says continuing, and then it says, let's play a guessing game, make a guess. So in my head right now, what am I expecting? What am I kind of hoping? I'm hoping that stir compare isn't comparing like A with B just statically every time. Hopefully, either RDI or RSI will be pointed at tests because that's what I input. I'm hoping that my input is flowing in through the program into this stir compare. And more importantly, I'm really hoping that that other thing is the correct answer that's going to make it say something other than you lose. I put test in here. We've got RDI, we've got RSI. These are two addresses. As you get more familiar with this sort of thing in like memory layouts, you'll notice like this 7FFFFF thing. This is a stack address. So this doesn't really matter. This isn't what our question is, but something that'll eventually just kind of pop out at you is like, oh, this is a stack address. And this 55555 thing, you're going to say like, oh, that's a data address. Like eventually, this is why we do it like a lot. We do lots of practice. So certain things just start feeling more natural as you get more experience with this. Now, I don't care what the address is though, right? We're doing a stir compare. I'm expecting there's two strings being compared, hopefully ASCII strings, and hopefully one of them is what I passed. So instead of printing RDI, just like the value as hexadecimal, I want to examine or like pull out of memory as a string, so x/s, before we did like pull out of memory as 8 instructions. In this case, we're doing pull out of memory as a string, RDI. Okay, so our input, unless we got really unlucky, unless it's always comparing the first thing as being test and we just happen to get unlucky and type test and it was comparing test, hopefully not, we could do a second run through and make sure that this first argument changes in response to what we put in. Now the second thing we can pass in is our SI. Okay, so let's go off of human intuition again here, right? Human intuition. We are comparing the strings test with super secret. Hopefully what's going on in your mind right now is I really want to put super secret in as the input on my next try because that's probably influencing the control flow. Probably this is the correct guess, and we can see that. So let's go ahead and do that. Let's just leave GDB. We're so confident. We don't even need to like follow it through. We don't need to see the compare instruction happen and the jump if not equal and all that stuff. We're like, all right, we already got our answer. I'm so sure of what I need to put in here. So let's run the program and let's put in the guess. It says you win. We won. So it didn't say you lose, it says you won. So we found a different branch that reacts to our input. So One interesting thing to be conscious of is that I actually took us down a slightly more difficult path for solving this. If we think back to building a web server, when we were putting something like HTTP 1.1 200 OK in the data section, and we were outputting that. That being in the data section means that that string, HTTP 1.1 200 OK, that thing is in the ELF. It's like those bytes are sequentially in the ELF somewhere. If we run hex dump, so I said before, or even cat, actually. I said before, catting this is like dumb. Why would you cat this, right? Because look at this. What is this? This is terrible. But somewhere in here, we gotta have super secret, right? Because it's doing a compare with super secret. All right, this is real bad. This is not how you would normally do this. We're saying super secret would be in here. SUP3R. Look at this. In here, this data that it was outputting, somewhere in this blob of mess, right? Most of this is like x86 instructions. Somewhere in here is the data that's being able to be output. So we see the string in this ELF, just catting the ELF. Let's play a guessing game. Make a guess, :space. Turns out the next thing is super secret, right? And then the next thing is you win. This is just a bunch of data that lives in the programs that you can printf on and such. We'll also notice there's a what ? That's impossible. We haven't seen that occur, so turns out there's more than just super secret in here. And then we also see you lose as data in here that was previously output to us. So we've seen all of these strings with the exception of what that's impossible. And so I didn't even need to run GDB in this case. I could have just looked at the data section, and this is a way of looking at the data section, just literally catting the ELF, and just like, again, used human intuition that of all the things in the data section, well, one of these things is the password, one of these things is the correct guess. So if you look at this thing that has like leet speak to it, right, maybe that feels a little more passwordy, more correct guess-y, and you could have just tried this. We could have also, I mean, maybe it's like that's impossible is the correct answer, or like, I don't know, something else. This is not the normal way that you would do this sort of like string analysis on the program. There's a program called strings, and strings will do this. It will just look for any sequence of ASCII bytes in a row and print that to you. I think it's by default at least 4 ASCII characters in a row. Maybe it's 5. We could read the man page. And this will just tell us all of the sequential ASCII bytes in this thing. So a whole bunch of them are like symbols and stuff. So it turns out like libc.so.6 is somewhere embedded in this ELF file. And that's because this is how it knows how to open libc.so.6 and load in libc. We can see gets and puts are actually in here because the symbols for them are in there, blah, 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 blah. But right in here, this is the data section. Probably. I mean, it turns out that it is, but in our heads, we're saying probably the data section. And it says, let's play a guessing game, make a guess, super secret, you win, what, that's impossible, you lose. So maybe with human intuition, you would have just like saw this using strings and done that. Alternatively though, like it doesn't matter how you get to the answer through your reverse engineering process. All that matters is that you get there. You might decide you really like static analysis. You might decide you really like dynamic analysis. You might decide that you like treating every program like it's a black box and I'm just going to guess the password. You might decide that's your preferred analysis strategy. Different things have different strengths, and just like certain strategies work well with different people. Turns out this would have been a good approach for figuring this out. Now, we saw that there's some other behavior in here that we haven't triggered, probably. Technically, this string could just be living in the ELF and this never gets printed to the user. But probably I'm thinking like, maybe this can be printed to the user or something. And we saw another stir compare in there. If we were really, really paying attention, we would have seen another stir compare in here. But this method of reading x86 instructions, this is like, it's a way that works, but I don't know about you, but reading, especially once we account for control flow, this is like kind of miserable because it's like all sequentially laid out, but really this is like a graph of control flow. And I would probably prefer, and you can almost like imagine building the program that tracks all the control flow and builds out a graph. Turns out someone has already built that program. That somebody is the NSA. There are a bunch of people have built similar programs. In this case, we're going to be using Ghidra, if you've ever heard of Ghidra before. We also have IDA free on here. We also have a tool called anger management on here. We don't have, I don't think, well, I guess there's a web version of Binary Ninja. Those are the four like popular tools. IDA free exists. The de facto industry standard. It turns out reverse engineering is like, you get really good at reverse engineering, this is a job worth like upwards of like over $1 million a year. Like this, if you get really good at it, it's a very sought after skill. And the most expensive tooling, the industry standard, is IDA Pro. We don't have that on here because it's like $10,000 a license or something. It's a very expensive tool, but it's for a very important job. Ghidra for our purposes though, and also if you want to use IDA free, all of these tools on here will work just fine for these challenges. Even objdump, as we showed before, you could do this all with objdump. In fact, when I first got introduced to reverse engineering like 5 or 6 or 7 years ago, we were forced to just use objdump. But we're not going to do that here. We're going to use tools that exist. Okay, what is this help screen? I don't think I've ever seen this. We don't need help. Okay. We are going to, let's see if I can remember how to do this. We are on the desktop, so I switched over to the desktop view. Alternatively, if you decide you want to install Ghidra on your own machine and you want to just like download these challenge binaries to your machine and not use the desktop in the browser, that's totally fine. Hopefully the desktop in the browser works just fine for us though. And then I am going to go to the file system. Well, no, I'm not. If we were going to look for the challenge, I would go into challenge, and we'd see here we got baby rev level 1.0. We're not doing that though. Instead, we're going to reverse this program that we were reversing, since we have some idea of what's going on here. And we are going to, we're going to drag that in. Is that not how this works? No, we need a new project. New project. Turns out the NSA is not very good at making good user interfaces, but they are good at making tools with very powerful analyses. Okay, we gotta say non-shared project. Okay, sure. Home hacker, we'll call this project test. Finish. Okay, now we feed the dragon, I think is what they say. The Ghidra dragon. Oh, there we go. Okay. And then it's saying you can just go with defaults. As soon as you see a box and you're like, do I hit OK or like, what do I press? Just whatever your mind like focuses on first, just hit that. And you'll probably be correct. This is saying, oh, is this an ELF? Technically, we could reverse engineer like a Microsoft or like a Windows binary, which is not ELFs. We can reverse engineer all sorts of different formats, but we're reverse engineering an ELF, specifically x86, little endian, 64-bit, assuming, I don't know, something to do with GCC. It probably detected that, this thing was compiled by GCC, and it's doing like extra analyses based on the fact that this thing was compiled with GCC. I have no idea how it figured out it was compiled by GCC, but some signature in that ELF says that. We'll hit OK. Now the dragon is chomping away, doing its analysis. Let's see here. Results summary. All right, we're just going to close that. Maybe we weren't supposed to close that. Double click that. Okay, here we go. Okay, here we go. Finally, something's launching. Test has not been analyzed. Would you like to analyze it now? Well, we'll just say yes, right? Just do whatever looks like the natural thing to press. We'll say yes. Turns out if you were analyzing a very big program, these analyses could take hours. So if you were going to, for example, another ELF program is Google Chrome. You could take Google Chrome and throw that in here and reverse engineer Google Chrome. But the analyses are going to take forever. That's why it's asking you. In our case, it's a very small program. It's like asking what analyses do you want to do. These tools, they're not very user-friendly. it's going to be fine for us. We'll just accept any default. Like, do we want to do condense filler bytes prototype? I don't know. We'll just default, analyze. Okay. Now, one issue that I'm realizing is how the heck do I make the text bigger? For your purposes, you probably don't need to figure this out, but we need to make this text bigger. Window, tools, window, whoops, edits, file, options for, maybe tool options. Text, display, fonts. Maybe here. 24, listings display. I don't know what the heck the listings display is, but hopefully that's the right thing. Okay, we'll roll with that. It's looking pretty good. Let's get rid of this box. Oh, the secrets. We're not supposed to show this yet. Guess it's showing that by default. Pretend you don't see that yet. Okay, so this is loading up all of it started us at main by default. So again, the user interface for this, I'm sorry, it's not so nice. If you don't like the user interface, use objdump. It's a very simple user interface. Print it out. You can copy and paste objdump, put it into Microsoft Word and print it and just read the assembly on a piece of paper. That's the best user interface. But if you want to try this tool, it turns out it's very useful. If I look over here on the left, there's like this functions thing. So it started me out in main, but I could see that this is main here, and I could click on this, and now I'm like definitely in main. So in the same way that we saw all of these instructions like we did with objdump, it's showing us all these things. It's doing some analyses. It's not actually just like straight up the objdump output. For example, we can see that it's like converting that RIP plus offset thing into this like S underscore let's play a guess, blah, 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 blah. We can see like it's doing analyses here already. But if I hit space, hold on. Window. If we hit window function graph, look at this, we've got ourselves a graph. So this is main. It does a whole bunch of instructions we can zoom in on. And when it does a jump, we can see that it can jump into two directions. It can go to here or it can go to here. This can fall through. I mean, we can start seeing the structure of this thing, right? So the first kind of thing that I said before is like, this control flow is a graph. Well, here's the graph. Now, I'm noticing now this graph isn't very nice. Hold on, let's quickly open just to show a difference. Let's show IDA free for a second here. Pretty sure IDA free, maybe that's the way to go. Because this is going to be much nicer. I was trying to think in my head that this semester we were going to try Ghidra. I'm going to tell you here, the reason that I was trying to switch to Ghidra this semester, you might like IDA free more because it's a $10,000 product, except this is the free version. So they care a little bit more about the UI. So this is IDA free. So you see this is a little bit nicer. I mean, sorry that the font is very small, but hopefully you can kind of see that there's x86 instructions printed and there's this nice graph. And this graph looks a lot nicer than that other graph. So that's pretty cool. The reason that this semester I'm trying to switch over to Ghidra instead of IDA free is that for all of you that are going to wait for the last day to do this assignment, and I know that half of you at least are going to do that. That's fine. That's fine. Last semester and the semester before, we're going to get to a tool called a decompiler here in a moment. And a decompiler converts x86 back to C. So if you like reading C, we're almost in luck here. The issue with IDA free is that when it does this conversion process, it's not running it on the box. It's doing what's called a cloud decompiler. So it's running it on some other server. It's sending like this x86 off to this other server to decompile it. And there's rate limits on that. In the last 2 semesters, on the day of the assignment being due, We have crashed IDA freeze decompiler on the cloud. It will crash. It will say cannot decompile, cannot decompile, cannot decompile. It's because when all of you are simultaneously doing this assignment in the last 2 hours before it is due, you are hitting their servers so hard that you crash their servers. And there's nothing we can do about that. That is their servers. We don't have the ability to run their decompiler. It's like a free service they offer. So it's up to you if you want to go down the IDA path or the Ghidra path or the anger management path or the objdump path. I'm just going to warn you now that I think IDA is probably the most usable, though Ghidra's not bad. IDA is probably the most useful, but when you wait to do this on the last day, you will not be able to decompile things, and you're going to be very sad, and there's nothing we can do about it. Okay, so there's your quick warning. Also, you'll notice that we're using like graphical interface programs. This also like pegs the cores in the memory way harder also, and things will melt. Please do not wait for the last day. You're going to be so sad. I know I say that for every module. This module, more true than any of the other modules. You will be so sad if you wait for the last day with this one. The server will be struggling very hard, way more than any other module. Okay, back to the Ghidra world though. So I'm talking about this decompilation thing. So I hit it briefly. It was kind of on the screen. This analysis is way better than just give me a graph of the control flow. This analysis is like, show me the source code. Why can this not go back? Here we go. Cool. Compilation going from C to assembly is like a one-way process. So for example, things like comments, like you put comments in your code, comments don't end up in the binary. Even function names might not end up in the binary. As I said before, all these symbol things, those symbol things can be stripped away from the binary. All that's really there is like the data section, and the text section is a bunch of x86 instructions. The C is gone, it's gone. But some really smart people figured out that there's control flow stuff going on here, and that everything's following a pattern, and that we can take all of this x86 and try our best to convert it back to C. It is not an easy task to do this. This is a very active field of research, in fact. But for those of you that would rather read C than x86, and it is not an exact science, this code could lie to you or actually be more confusing than assembly, as you will learn throughout this module. But in this case, we've got something going on here. This is like kind of readable, right? Hold on, let's see if we can zoom in real quick. Tool options, fonts, decompiler. Where the heck is the font size? Can I just like, can I hit plus? Oh, what the heck is that? What am I doing? All right, we're gonna roll with this. I don't know what I'm doing here. But we can see, we'll even zoom in a little bit more. Well, that's too much. We can see that there's this C code. I'm gonna tell you right now, the C code is not the same as the original C code, but it's kind of nice and readable. It's a little bit better than x86 in some ways. For example, we can see that it says printf, let's play a guessing game, make a guess. Then it gets something to some variable. It's calling that variable local underscore 58. It does a stir compare with local underscore 58 and compares it with super secret. So immediately, like, just looking at these 3 lines of C, we probably figured out what we were trying to figure out originally. We can see that if that thing is equal to 0, it prints you win. So that's the behavior we observed. Otherwise, it does this for loop thing, and then it does this stir compare. And if that stir compare is 0, so if those things are equal, it says, what? That's impossible. Otherwise, it says you lose. So you'll see this for loop thing, like what the heck's going on with this for loop? So we have something that's equal to 0, less than 10, go plus 1, right? This is a standard for loop. If I hit, not that letter, how do I go out? I'm gonna figure out how to make this font size bigger. I right click on this thing and I hit rename variable. I can like interact with this decompiler, and I can start improving the results. So for example, local underscore 5c looks terrible. If you've ever written a for loop before, you've probably done I equals 0, I less than 10, I plus plus, or I equals I plus 1. Let's just call this thing I. And then we see there's this impossible thing, impossible sub I, and it's telling us that impossible, if I hover over it, well, it's either way, it's doing impossible sub I equals impossible sub I XOR 0x80. This XOR 0x80, this is like, it's not encryption, but we'll just call it encryption as the simplest possible thing we can call it. Really, it's just obscuring what's going on. We'll learn about proper cryptography later. It's obscuring the contents of this thing. And this is why we didn't see like another password in the binary, is that it has something encoded in the ELF, whatever this initial impossible thing is, and we're taking sub I and XORing it with 0x80. In other words, we're flipping the highest bit of each byte. And in ASCII, the highest bit is always a 0. So the way that this was encoded, I'm just going to tell you the way we wrote this program, is that we set all the high bits to 1 intentionally, and then this is flipping them all back to 0. So at runtime, it's like decoding. What the heck happened to the camera? Oh boy. Oh no, now it's sad. Too much pointing. Oh boy, I think it's sad. We'll just do it manually. At runtime, we're modifying this thing back into the password. So it's not a static password. It's changed at runtime. And you'll see in these challenges, this is the type of thing we do that you're going to have to figure out how to reverse engineer. So it does this operation on this impossible thing. We compare if it's impossible. It says what? That's impossible. Else puts you lose. So that, I mean, of course, this is probably much more readable than reading a whole bunch of x86 instructions. In this case, though, I mean, I'm still thinking to myself, I mean, if I double click on this impossible, we'll see, how do we go here? Maybe we go over here. Labels. Where are you, impossible? Impossible. Hold on. I'm starting to think this Ghidra idea is not inspiring confidence. There's a way in this tool to investigate impossible. But either way, this probably is more difficult. If we think back to the C, right? So if I hit G, I can type G main. If we look back to this, we can do this in exactly the same way we did it as before. We can just figure out what the heck's going in this stir compare, right? That's all we care about. Once it's done this task of like unencrypting it, again, it's not really an encryption, but unmangling this thing, we can figure out what it is. So real quick before we end, let's do that real quick. Look how quick we can do this. We just type break stir compare. Where do we want to break? We want to break a stir compares. Start this thing. Wait, what? Break. Hold on. X8I RAP. Oh, wait, we're in stir compare. Continue. Continue. Hold on. Restart real quick. Start. Break stir compare. Continue. Let's make a guessing game. Hello. X/S RDI. So the first thing. The second thing. Okay, we're comparing hello as super secret. Continue. We're in the second stir compare now. X/S RSI and RDI. Well, guess what? Here's our second thing, this impossible thing after we've like fixed it up. And it wasn't in the ELF, it wasn't printable before because we did this like little manipulation at runtime. This thing, now, if I run it, so if I run /test and I put this thing in now, it says what? That's impossible. So this is a quick primer. There's a lot going on here, I know, of static analysis with objdump, static analysis real briefly with Ghidra. We'll dig into it more. There's a lot more to get out of that, to get out of Ghidra. and some dynamic analysis with strace. We found strace maybe wasn't so useful in this particular case. In other cases, it depends what you're trying to reverse engineer. In other cases, strace could be incredibly useful. And GDB. So we figured out stir compare was kind of our thing. I don't know about you, but probably the simplest thing was like, what the heck's going into our stir compares to figure out what's going on here. Looking at the C source code, though, is pretty nice in Ghidra. And if you are wondering what the heck was going on this entire time, if like all your assumptions about this program are right after we've discussed it, this is the program. So maybe this makes it make more sense, right? If we go back to what the heck this thing actually was, this is what I wrote. So I wrote impossible equals this. So this is this string with all the 8 bits set to a 1. So that's why it was not printable with strings. Grab a buffer, we say, hey, print this, get some input, compare it with super secret, say, well, I changed the code actually. I think I didn't recompile it before class. You win, right, is what it says. Otherwise, we do this thing where we go from 0 to the size of impossible I plus 1. We're just XORing it back with 80. We're turning it back into ASCII. We're not storing it as ASCII. We're storing it in this weird thing. Then we compare with that what that's impossible. Otherwise, you lose. So if that was what, after all this reverse engineering was in your head, that was your mental model of this program, that's what we were analyzing. So this was the original ground truth of it all. All right, thank you all for attending, and good luck.